example, a physical change or a chemical change. So what would chopping wood be? Physical, right? Because in theory, although that would be a C, in theory, you should be able to put it back. I mean, it might require a little bit of work, but physical change, grilling a steak, getting it well done. What do you think? Chemical, okay? Can you put it back? Can you turn it back into the raw steak? No. So that's going to be a chemical change. Boiling water. Physical, because like you could condense that steam back into water. So that's a physical change. Disinfecting a cut with peroxide. So if you've ever cut yourself and they take and put peroxide on the cut, what is that? Chemical. Why? What do you see? The bubbles, right? So it bubbles and sizzles and everything. That's actually reacting with that tissue. So that is a chemical change. Getting a haircut. Physical change. Digesting food. Chemical. Okay, so just some examples of things that you might see. And just keep in mind, if it's physical, you could like heat it, cool it, push it back together. You could do something to change it back to its original condition. If you can't do that, then it's going to be a chemical change. All right, so when talking about burning charcoal, you can write this as a chemical reaction. And there's a bunch of ways to write chemical reactions. The first one is kind of just using like this idea of like, okay, you see like if you took this gray ball and you took two little red balls, in theory, you could combine them to make a unit. Well, that's a chemical change because what we end up with and what we started with, they're two different things. If you wrote it as a chemical equation, then you would use the names of the elements just using the symbols. Remember that the arrow is kind of what splits your starting material and your ending material. Okay? So I always kind of think of everything in front of the arrow is what I start with, the starting material or reactants. Everything past the arrow is going to be the products. And you might have 5 reactants and 1 product, or you might have equal numbers of them, or you may have a lot more products. Just remember that arrow is like the divider line. If you see it this way, you might see in parentheses letters S, G, L, or even A, Q after an element's name. All that's doing is telling you the state. Okay, so if you see C with a little s, that's solid. G is gas, like what oxygen has. If you saw like water, sometimes it's written H2O and you'll see this little parentheses L, that means it's a liquid. And if you have something like salt dissolved in water, so it's dissolved instead of being a solid, and so if it's dissolved, they use the term AQ. So those are kind of like the 4 different ways that you will see them described. It's really just telling you what the component states are in the reaction. So the big thing is that the number of atoms of each element type on both sides has to be the same. So this is what they call a law of conservation of matter. So in this one, when charcoal combines with oxygen, it forms carbon dioxide. And do you see that if you look at the little balls at the top, 1 gray ball on either side, 2 red balls on either side? I could do the same thing with this chemical formula. C all by itself means that I only have 1 carbon. O2 means that I have 2 oxygen. And I will just tell you that I write oxy because if I write 2-0 or 2-O, it looks like 20. And that sort of throws you sometimes. So I always just write OXY. But if I look on the opposite side, CO2, according to its formula, how many carbon? There's 1 carbon and 2 oxygen. So just based on the formulas, comparing, I see that I have 1 carbon on both sides, 2 oxygens on both sides. So you would say that this is balanced, which means that 1 carbon plus 1 oxygen molecule will combine and form 1 carbon dioxide. So really, the number in front is called a coefficient. And if it's already balanced, then they're all just 1s. But that doesn't always happen, okay? So remember, we got stuff like solids, liquids, gases. Don't worry, you don't have to balance if you see the little parentheses S or G or L. You don't have to worry about that in balancing. It's just telling you the state. You do have to follow this law of conservation of matter, law of conservation of mass, meaning that both sides have to be the same. So if I was, like the example that we did, it's exactly equal. But what if I was to talk about making water? So hydrogen plus oxygen combines to form water, which would be a liquid. So in this, again, everything that's to the left of the arrow is the reactants. Everything to the right of arrow, those are products. So the rules to do this is if you've done balancing equation, if it hasn't been all that long, you can they're kind of like a puzzle. You can kind of do them in your head. But if you haven't, or it's been a while, or it's always been something that kind of frustrates you, here's the steps to do this. So first, I always just draw a line through the arrow because it helps me to see that I got to split them. I know I got to list based on the formula how many atoms on the left side, how many atoms on the right. So H2 would be 2 H's, O2 would be 2 oxygen. So that's the reactant side, and it's just based on the formula. H2 means 2 hydrogens, O2 means 2 oxygens. Over on the product side, I have H2O, which tells me that I have 2 H's and only 1 oxygen. So do you see that they're not equal? Based on their formulas, they're not equal. I now have to figure out what is the ratio that the reactants and products have to react in so the total number of hydrogens on both sides, the total number of oxygens on both sides are the same. Okay? So you draw the arrow and just list the number of atoms based on the formula. So now you look to find what is an atom, an element pair that are not balanced. And then this one, it is oxygen. Okay? So it's always going to be the smaller number. I'm going to have to multiply the smaller number times something in order to balance it with the larger number. So in order to make this a 2, what do I need? Multiply it times 2. So I've got to go times 2. That's going to give me 2 oxygen. That 2 is the coefficient. Okay, so whatever I have to multiply it by, that number has to go on the line in front of the H2O in the chemical formula or in the chemical equation. But now, see that 2 means that everything in that molecule is multiplied by 2. So what else do I have to multiply? I have to multiply the hydrogen by 2 because it's 2 H2Os, which means double the hydrogen and double the oxygen. So then this sort of gets people because they were like, well, it was already balanced. I don't want to change it. I just want to leave it alone. Well, they have to be balanced. And so if you start off and they're balanced and then in your balancing you unbalance something, just go back and balance it again. So does everybody understand this 2 is what I put here? Okay? I have to multiply H2O, both the hydrogen and the oxygen on the right side by 2 because the coefficient is in front of that molecule. All right, so then, am I done? No, because now oxygens are balanced, so that's good, but now hydrogens are not. So I'm going to have to change which side, left or right? Left. You're always going to change the lower number. It's a 2. Over on the right side, it's a 4. What do I have to multiply my hydrogens by to have 4? So if I multiply this by 2, that gives me 4 hydrogen. That 2 goes in front of the hydrogen. Do I multiply that oxygen by 2? No, because they're separate molecules. I only multiply the formula in front, behind that coefficient, so just the H2 gets multiplied by 2. And then when I go back and look, 4 hydrogens, 2 oxygen, so that is balanced. Now I didn't change the oxygen on the reactant side, so that means that would be a what? Just a 1, okay? You don't have to change all of them. You're only going to add those coefficients to try and get the total number of atoms on both sides the same. And if any of them aren't changed, just put a 1 in front. You could leave it blank. A lot of times you'll see it's left blank, like in our example before. But my suggestion, I always check it. And if I'm sure, then that way I put the 1 and I know that I've checked it. So I know that I've checked all of my atoms. Okay? So let's do these 2. So draw your line through the arrow. List the number of atoms according to the formula on each side. Remember that the goal is to make the total number of each atom the same by adding a coefficient to the ones that are not balanced. Okay? So first thing, draw the line. Second thing, list how many atoms in each formula. So magnesium is going to get a what? 1. Nitrogen is a 2. Over on the product side? 3. And 2. Right. So when you look at this one, do you see it? You're like, oh, nitrogens are already balanced. I only have got to balance the magnesiums. Nitrogens are already 2 and 2. So if I'm going to balance the magnesium, which side do I need to change? The left. What do I need to put in front of the magnesium? A 3. So I've got to go times 3. I try to change colors so that I think it shows up a little better. That's going to give me 3 magnesium. Now that 3 goes on the line in front of magnesium, but notice it doesn't affect the nitrogen on that side because they're 2 different molecules. So what do I got to do next? Do you see, are they balanced? Yeah, do you see 3 magnesium, 2 nitrogen, 2 nitrogen? So once you check it, you're like, okay, those are just ones. You don't always have to change all the coefficients. So what about this one? So when you look at this one, draw a line. What does it mean when you see the parentheses? No, I've still got a list. So how many aluminum in this? 2. So I have 2 ALs. Now how many carbon is that? 3, because I have 3 CO3s. Remember in math, if you have a parentheses and a number outside, everything inside is multiplied by that number. So that is going to be 3 C's. And how many oxygens? No, times. Make sure you multiply them, right? So it's like 3 CO3. So I have CO3, 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 which gives me 3 carbons and 9 oxygen. Okay, so put yourself a note. So if I have like CX and Y, and I have that 3 on the outside, then whatever my number here, that carbon is going to be X times 3. And the nitrogen will be whatever the Y is times 3. Okay, so you're always going to multiply the number by what's outside. What about on the other side? So Al2O3, what does that tell me? 2 aluminum and 3 oxygen. And then CO2. 1 carbon and 2 oxygen. Now notice that you have oxygen in 2 molecules on the product side. I add like a little bracket because that reminds me, oh yeah, those are the same. So I'm going to need to make sure the total number of oxygens on both sides are the same. However, balance those last. I call those the more complicated one. Always balance the simplest. So, like see aluminums in one place on either side, carbons on one place and on either side. Balance those first. Balance the oxygens last because they're the ones that are going to be more complicated being in more than one molecule on either side. So, what about aluminums? They're already balanced. You see that I have 2 and 2? So you're like, oh, well, those ones are done. Okay, now check the carbons. They're not. So which side do I change? The right side. So how do I end up with balanced carbons? Multiply it times 3. So I've got to multiply that carbon by 3. Remember that 3 goes in front of the CO2. But that means I'm not just multiplying the carbon. What else am I multiplying by 3? But not all the oxygen, just the 2 oxygens that we have here. So that's going to give me 6 oxygen. Okay, so whatever you put as the coefficient on the line, all of the atoms in the molecule behind it are going to get multiplied by that number. So now go back and count. Aluminums are still balanced. Yeah. Carbons. Yep. Now oxygen. So I have 9 oxygen on the left. How many oxygen do I now have on the right? Do you see that? So I have 3 and 6. So 3 and 6 is going to give me 9 oxygen. And that'll happen a lot. Not every single time, but many times if you balance the simple atoms first, then you will find that the more complicated ones, the ones found in multiple places on one side or on both sides, they'll balance themselves, okay? So just try and balance the simplest ones first. So I'm going to give you a minute. Work on these 3. Get as far as you can. You can talk with your elbow partner or person across from you. You can check as you finish them. Check with them, see what they got. Should have gotten this far, right? This is just basically like making the list. Making the list based on the formula for each of them. Now, the thing before you start balancing, I suggest that you go back and any that are found in more than one place, group them together. Just so that you remember to go back, because the total number of hydrogen, total number of oxygen on both sides have to be the same. And I'll tell you, it's almost always those hydrogens and oxygens that end up doing this. So just kind of like put a little bracket to connect them so that you remember in your head, I got to add the total number at the end. They've got to be equal. So in this first one, so when you look at the first one, you want to balance the simplest ones first, right? And so you look at which ones. Which ones are only found in one place? Oxygen, they're 1 and 1. Well, that's balanced. And then also the Na, sodium, and that's found in 1. It's already balanced. So that leaves you with no choice but to try and balance the hydrogens. So the thing to look at this one, the side that only has 1 hydrogen in a molecule is over on the left, and it's a 2. So that's an even number. So do you notice over on the right, I have 3? So which of those hydrogen numbers should I change in order to be able to have an even number? Do I want to change the 2 or the 1? If I change the 2, it's still going to give me an odd number, right? Because it would be like 4 plus 1 would be 5, or 6 plus 1 would be 7. But if I could change that 1 here, if I can change this hydrogen and make it an even number, then I know I can balance like 2 with 4 or 2 with 6. So I can balance. They have to be even though. So if they're found in more than one place. Okay. So in this one, the first one that we'll do then is we're going to try and balance this hydrogen. I want to make this a 2 so that I'll end up with 4 hydrogen on the right side, and then I can balance it easily with the 2 hydrogen on the left. So if I put that 2, that's going to give me 2 hydrogen. Where do I put the 2? It needs to go in front of the what? That NaOH. So I got to put a 2 here, but that means I'm not just multiplying the hydrogen. I have to multiply the sodium by 2, the oxygen by 2. And then this is the part where you're like, well, I just messed everything up, right? So now nothing is balanced, okay? But now I have a point where I can balance these. So go back and balance the simple ones first. So which one would you balance next? Balance the sodium, okay? So in this, I have 1 sodium on the left, 2 sodiums now on the right. So what am I going to change? I'm going to change the left. So I've got to make this times 2, giving me 2 sodium. That 2 goes on the line. So now sodiums are balanced, 2 and 2. How do I balance the next one? Okay, so I'm going to balance the oxygen next. I need to have 2 oxygens on the left side. So So I have to multiply the oxygens by 2. So notice when that puts that 2 in front of, it's not just the oxygen, it's 2 in front of water. So that means I have to multiply the hydrogens times 2 as well.
I have a question. I got different numbers for the coefficients, but mine balanced out.
So what did you end up with? Did you end up with 4, 4, 2, and 4?
I ended up with 3, 3, 2, and 3.
3.
Yeah.
Okay, hold on. So you had 3, 3, 2, and 3. Okay, so I see sodiums are balanced 3 and 3 on both sides. So this hydrogen, you would have 3 hydrogens here and 4 hydrogens here, so I'd have 7, but over here I only have 6.
Yeah, I see that now.
Okay? So in that one, do you see that? Yeah, I see it. Okay, so there are 6 hydrogens over here. So that's the part where in that one, if you have multiples and one side has an even and the other one has like an odd number, if you can fix the odd to an even, then it's just gonna make it all like fall right into place. Okay, so that's one way, but yeah, those ones, the hydrogens wouldn't be balanced in those. All right, so let's try the second one. So, which did you choose to balance first? Oh, go ahead. Okay, so if you get this, do you see that it's right? Like if you went back and counted, you would just have twice as many and it would be fine. But when you balance an equation, you always want the simplest whole number ratio. So when you get done, if you could divide all your numbers by 2, simplify it, okay? So that would just simplify it. And like, I had that happen. I usually like take a point off because, I mean, you did balance it, you just didn't simplify it at the very end. So in that, if you get a number where they're all even numbers, go ahead and simplify. Or even if you got like 3, 3, 6, and 9, you could simplify those, okay? That's the only difference with these is they could all be divided by 2 and all equal that number.
When you said 3, 3, 6, and 9, when you said simplify all of those?
Right,
how
3,
would you
3, I
simplify
divide them
that?
all by 3.
Oh,
3, 3.
okay.
So like if I got an answer and it was 3, all numbers that were divisible by 3,
Okay.
that would be another possibility that you might sometimes get. Usually you'll just see that all your numbers are even. So then just go back and you can simplify the coefficients. Just make sure you balance it first. Okay? So in the second one, which one did you choose to balance first? The Al, aluminum. Okay? Do you see aluminum's in one place on either side? Sulfur's in one place on either side. I would not balance oxygen first because you see oxygen is in every single molecule, okay? Leave that till absolutely the last. We might have to use the hydrogens because it's in one place on the left, 2 places on the right, but I want to balance the simplest ones first. So how did you balance the aluminums? Which side did you change? The right side. In order to have 2 aluminums on the left, I need 2 aluminums on the right. So that means I have to multiply that aluminum times 2. That means the number goes in front of the molecule that has the aluminum. But now that means AlOH3 all gets multiplied by 2. So times 2 times 2. So now I got 2 aluminum. 3 times 2 is 6 oxygen. 3 times 2 is 6 hydrogen. So now balance the next simple. So which one's that? Do you see that? Not the hydrogen. Hydrogen's found in 2 places on the right side, only 1 place on the left. The sulfur, S, okay? So sulfur is the one, see that sulfur is only in 1 place on either side. So balance that one the next. So which side do I need to change? The right, because I have 3 on the left, only 1 on the right. What do I have to multiply that sulfur by? Times 3. That's going to give me 3 sulfurs. That means I got to put that 3 on the line in front of H2SO4. So I put the 3 in front of the molecule that has the sulfur. That means everything in that molecule gets multiplied by 3. So I'm going to have to go times 3 times 3. Now I have 6 hydrogens and 12 oxygens here. It didn't mess up the aluminum. Always go back. The simple ones need to stay balanced. Aluminum's balanced with 2 and 2. Now sulfur is balanced with 3 and 3. So the next one to balance is what? The hydrogen. So do you see that the hydrogen's only in one place on the left? So I'm going to balance the hydrogen next. So to balance the hydrogen, which side do I need to change? Got to change the left. Left side I have 2. On the right side, how many do I have total? 12. Do you see that there's 12 hydrogen on the right side? So how do I make this 12? Got to multiply it by 6. That's going to give me 12 hydrogens to balance the hydrogens. That means that 6 goes up here. So what else do I have to multiply by 6? The very bottom oxygen on the left. That's going to give me 6 oxygen. Okay? So whatever number you put on the coefficient, everything in that molecule gets multiplied by that number. So then you're like, good grief, there's a lot of numbers. Okay, so is aluminum still balanced? Yep, sulfur still balanced. Now hydrogens are 12 and 12. How many oxygen total? I have 12 and 6. So over here I've got 18 oxygen. And then let's go count these. How many? 18. So see what I mean by if you balance the simpler, the one that looks like, geez, I'll never be able to figure that one out. They'll just fall right in. They'll balance themselves if you balance the simpler ones first. Okay, so what about the last? Last one looks like super simple, right? It's all just ones. Which one do you want to balance first? You can pick because they're all found singly. Oxygen, okay. So which side did you change, left or right? Left. In order to have 2 oxygens, I've got to multiply this oxygen by 2. That means the 2 goes on the line. That means I also multiply the hydrogen by 2 because it's 2 H2Os. That's going to give me, not 2, that will give me 4. 2 times 2, so I have 4 hydrogens. Okay? What did you balance next? Okay, so you got to pick one. Don't try to balance like the whole thing. Did you balance the H's or did you balance the Cl's? Okay, so you balance the Cl's. So on the left, I have 2. On the right, I have only 1. So what do I need to do? I need to multiply the right side. So I'm going to multiply the right side times 2. That's going to give me 2 Cl's. That 2 goes up here. What does that do to that hydrogen? Going to multiply it by 2 as well. So I'm going to have 2 H's over on that side. Am I done? What's not balanced? Hydrogen. Okay, go balance the hydrogen. How many on the left? 4. Okay, so I have 4 hydrogens on the left, 2 hydrogens on the right. So what am I going to have to do? So this 2 hydrogens, I have to multiply times 2 more in order to have 4. That means I put another times 2, whatever you multiply, even if you do it more than once, just add that into the coefficient. We can change it at the end. But what else do I have to multiply by 2? The Cl. So now I have 4 Cl's. So am I good? Done? No. What do I have to go back and change last? So can you see that I have 4 Cl's and only 2 on the left? So what do I have to multiply that Cl by? Times 2. That 2 goes on the line, gives me 4 Cl's. Now am I done? So the blank gets a 1. And this 2 times 2 becomes a 4. Okay?
In our second one, does that AL2 get a 1? The second example?
Oh, up at the top, yes. Yeah, any blank. Sorry, I left that one blank. I do try to usually go back and fill them in. But if you leave it blank, I don't count that wrong. Like if it's a 1 and you leave it blank because you know it's a 1. But if it's supposed to be a 2 and you leave it blank, then that's wrong. Okay, but 2, 2, 4, and 1, do you see that those are the simplest whole number ratios? Okay, I can't simplify that one any further. All right, so I'm gonna leave, there's like a couple of other ones I want you to practice. In fact, in that handout, remember the handout that had the last page was the periodic table? Everyone will make this the first page. So the last page is the periodic table. The next to the last page is 2 pages of balancing equations. Okay, so if you're familiar, comfortable with this, run through these ones. There's a couple that are kind of challenging. Like even my like little chemistry tutor was like, that one took me a long time to do. Well, you know, there's a few out there that are a little bit challenging. So if there's a few you can't do, I'm not gonna put those ones on the exam. The ones you're gonna see are gonna be kind of like sort of straightforward ones that we see, ones that we've practiced. The answers to these, to the handout, those are all posted in Moodle. So if you go into the first exam module, it says balancing equations and unit conversion worksheets. The answer keys are posted there. So if you're doing them and you're like, I think I got this, go ahead and check yourself. See if you're actually doing them right. We'll do a couple more of them on Thursday just to see how far along everybody is doing. So I've got a bunch, but I want to get into the math part. So this is what I would consider kind of the middle section. The beginning of chapter 1 is really all this intro and then kind of leads into balancing equations that you may or may not have done or remember. The middle part, though, is really this basic math, but it's all metric. So if you're really familiar with English units, then this can sometimes be the struggle. They went to metric. It's called the SI, or the International System of Units, the fancy way of saying. So metric was chosen because the sizes, they agreed on a uniform standard size, and then everything is different by powers of 10. So if you multiply something by 10, you just add a 0. If you divide something by 10, you move your decimal place to the left 1 place. If you multiply times 1,000,000, you add 6 zeros. So it's really just this moving of a decimal place instead of having to remember how many feet in a yard, how many inches in a foot, how many feet in a mile, right? How many ounces in a quart, like remembering all those. In fact, if you're in lab, if you're taking the Chem 130A lab, tomorrow we get to do a lot of English practice unit conversions. It's very long, okay? But hopefully it kind of gets you into doing the process of converting from one unit to another. As long as you're doing it exactly the same, it really doesn't matter if we're talking about mass. The standard unit for mass is the gram. And literally, a gram is about a 1/4 teaspoon of salt. Okay, like a good pinch of salt, that's about a gram. It's pretty small. Most of the time we talk about kilograms. Kilograms is about 2.2 pounds. We can talk about so kilo is a way of talking about a bigger unit. But we can also do the exact same thing and use the exact same prefixes for volume. And volume is probably the most familiar to people because of soda, right? So in like the 80s, the 2-liter bottle came out. That was like, ooh, wow, large volumes of soda, just what we all need, okay? So most people kind of in their head kind of have an idea about what a liter is. We can go scaling up or scaling down just by adding a prefix. So we can have kiloliters, we can have milliliters, we can have deciliters, just like we can have milligrams, kilograms, and decigrams. Last one, length. So when talking about length, the standard unit for length is a meter. And a meter is like just over 3 inches longer than a yard. So if you kind of think about a yard. So meter is this length. If we want to have much larger lengths, like close to miles, we use kilometers or kilometers. But we can also measure things that are smaller in length. So we can have what's kind of like an inch, about 1/2 inch. That's a centimeter. Or we could have decimeters. Or we can have micrometers when we start talking about like microscopically small sizes. So what this metric system does is it starts off with 3 base units, gram, liter, and meter, whether you're talking about mass, volume, and length. And then we can use the exact same prefixes to indicate larger and smaller sizes. So in here, really, there's only 5 prefixes that you need to memorize, okay? They do have more of them listed, but I will tell you, you will rarely see giga or mega, because those are like really large measurements. But it's pretty common to see kilo as a prefix. So the term kilo, K-I-L-O, put in front of a gram, meter, or liter becomes a kilogram, a kilometer, or a kiloliter. And what it means is that it is 1,000 times larger than the base unit being gram, meter, or liter, the prefixless base unit. So if I have 1 kilogram, that means I have 1,000 grams. If I have a kiloliter, it's 1,000 liters. If I have a kilometer, it's 1,000 meters. So kilo means that it's a larger measurement. Kilo always gets the 1, and the base unit gets the 1,000. The other ones, though, the other 4, are all smaller. Deci, D-E-C-I, put in front of a base unit, tells you that it's 10 times smaller. I always think of like a decimal. Like you go 1 decimal, that's deci. So it's 10 times smaller. So this means I have to have 10 decis to make 1 base unit. So 10 deciliters is 1 liter. I could substitute meters in there, or I could substitute grams. 10 decigrams is 1 gram. 10 decimeters is 1 meter. So the term deci means that it's a tenth or 10 times smaller. Centi, I always think of like a century, or how many pennies in a dollar. It means it's 100, right? And a century is 100 years. So centi, this is 100 times smaller. So it takes 100 centiliters to equal 1 liter. 10 centimeters is 1 meter. Or sorry, 100 centimeters is 1 meter. The last two. So the last two are getting really small. So we have milli. And so remember I said if you're talking about mass, you use grams. And grams, its abbreviation is always a G. If you're talking about volume, you're talking about liters, and its abbreviation is always an L. And oftentimes I capitalize it just because it doesn't look like a 1. But if I'm talking about length, the base unit is the meter, and they use a little m. So this sometimes throws people because milli is a little m as well. Okay? So a prefix has a little m, but then your unit of measurement can have a little m as well. Milli means that it's 1,000 times smaller, like the millennium, 1,000 years. So it takes 1,000 millimeters to equal 1 meter. And that sometimes throws people because they're like, wait, which is the milli and which is the meter? How do I know? So just remember, if you only see 1 letter, then it's always meter. Okay? If it's a single prefix, it's always meter. If you see 2 M's, then you know it's millimeter. Okay? Or if you see an M and a G, then you know that's milligram. So if the M's in front of another letter, whether gram, liter, or meter, then you know it's milli. So the prefix will always have 2 abbreviations. So like this, 1 kg equals 1 G, or sorry, 1,000 G, Lord, will equal 1,000 G. 1 kilogram is 1,000 grams. Or you might see 10 DL is equal to 1 L. Okay, so notice if it's a prefix, it's always 2 letters. If it's just the base unit, meter, liter, or gram, it's just a single letter. And those are what I call those ones. I call those base units. Base units don't have a prefix. Meter, liter, and gram are kind of what everything is based on in mass, length, and volume. Last one, micro. So not only do you end up with a base unit with an M, and then you end up with a prefix unit that's got an M, then they use another word that starts with M. You really think they could have like come up with some other ideas, okay? So they literally ran out of M's. So in this, for micro, they go to the Greek symbol that is called mu. So the symbol for this, it is 1,000,000 times a 1 with 6 zeros, super, super small measurement, whether mass, length, or volume, and they use the symbol mu. And it looks like a U with a little foot. Okay, so that's that sign. That is the mu. So don't let that throw you. It kind of looks like a funny U with a little foot off of the front. It takes 1,000,000 micrograms to make 1 gram. So these are the only ones you need to know for this class. If you memorize what these prefixes mean, you can do any kind of unit conversion because they kind of went to like a standard. Everything changes by factors of 10, which just means you just have to move decimal places. It's really much easier than trying to remember all of those number values for conversion in English units. So because they're equal, like deci, 10 decigrams is 1 gram because deci is 10 times smaller. So anytime you have deci in your term, you know that a 10 is going to go in front of whatever term it is. Doesn't matter if it's decigrams, deciliters, or decimeters. Deci gets a 10. I can write it 10 decigrams per 1 gram. It's kind of like saying 12 eggs per dozen, right? So everybody knows that there's 12 eggs in a dozen. So if you're saying get 12 eggs, or if you say get a dozen eggs, it's saying the same thing. Well, that's what this is saying. This is saying I could say 10 decigrams, or I could say 1 gram. I'm saying the exact same thing. I'm just using different units to do it. If I have centi, centi will always have 100 because centi is 100 times smaller. It always takes 100 centis to make a base unit, whether it's grams, meters, or liters. So I could put grams here, or I could put an M, meters here, or I could put L for liters. Anytime you have centi, you're going to put 100 in front of the C. When I'm talking about milli, what am I going to put in front of the M? 1,000. 1,000 M, milli, gets 1,000, base unit gets the 1. So it's 1,000 milliliters in 1 liter, 1,000 milligrams in 1 gram, 1,000 millimeters in 1 meter. Micro. Yeah, so when you see a micro, so for example, 1 meter, this would be 1, 2, 3, 4, 5, 6, 1,000,000 micrometers. So notice whether the micro is on top or the bottom. In front of micro, you would always put 1,000,000. Milli always gets 1,000, centi gets 100, deci gets 10. The only oddball is that 5th one, kilo. Because kilo is not smaller, kilo is bigger. So if I have a kilo of anything, 1 kilogram would equal 1,000 base units. So kilo always gets the 1 because kilo's the bigger value. Kilo is a much larger, like I said in this, a kilogram is like 2.2 pounds. Remember I said grams like a big pinch of salt. So it takes 1,000 big pinches in order to make 1 kilogram. Same thing if I have it flipped the other way around. So if I had 1,000 meters, that would be 1 kilometer, which is about 0.6, just over half a mile, right? So you know a meter is this big, right? Like kind of like a yard. So if I have 1,000 of these, it's just over a half a mile in length. So kilo is a larger measurement, so it always gets the 1 and the base unit gets the 1,000. Say that again? So what does this mean? It's meter. If there's only 1 M, it's meter. If there's 2 M's, it's millimeter. And if there's an M in front of a G or an L, then it's milli. But if the M's all by itself, this is meter. That's what I said, like getting used to seeing the abbreviations written that way, because I sometimes see people see like M and G and they go meter gram. No, it's milligram. Okay, so if you have those two, there's two letters. The first letter is the prefix. Second letter tells you what unit of measurement it is. And if it's all by itself, then it's an M. It's meter. So with this, okay, so like you could say 12 eggs per dozen. You could also put 1 dozen over 12 eggs. Do you agree that they would still be equal? Well, these are saying they're equal. 1 kilogram equals 1,000 grams, so I could put them this way or I could put them this way. And that allows you to convert from one form to another.
I'm getting confused, so it's not like math when it's like division, right? It's just like this.
Yeah, we're going to set it up that way.
Oh, wait.
Okay? Mm-hmm.
Okay.
Okay, so for example, let's just say that we have 12 grams and we want to know how many centigrams that is. So we're going to convert from grams to centigrams by using the equivalent, by saying, okay, well, how many centigrams in a gram? Okay, I'm going to set them up. So whatever you start with, they always call that the given unit. So in this, my given unit is 12 grams, okay? And keep the unit for the practice especially. So keep the unit. So my given unit is 12 grams. Then I'm going to multiply, put a times, and put a line. The unit I'm given always goes in the bottom in the first step. Because what'll that do? They'll cancel, right? So the given units are going to cancel. So G goes in the bottom. So grams goes down here. The unit I want to go to is centigrams. That's my desired unit or answer. Okay, so that's where I want to go. Now, anytime you see centi, what goes in front? 100. Right, so that's why I went back through that. Anytime you see deci, 10 goes in front of it. Anytime you see centi, 100 goes in front of it. Milli gets 1,000, micro gets 1,000,000. The only oddball, if you see kilo in the problem, kilo gets a 1 and the base unit gets 1,000 because kilo is so much bigger. So, do you see that now these cancel? Grams and grams cancel, and so my answer is what? My answer is in centigrams. Doing the math, you multiply everything across the top. This grams will get the 1. So 12 times 100 is 1,200. So we're going to do a couple that are pretty straightforward this way. Really, now you're going to do this. Okay, so I want you to set them up the same way. There's your given unit, there's your desired unit. Use the process, write it out, you've got space. And I wrote at the top, sort of like, those are the only ones you need to remember. Kilo, deci, centi, milli, micro. Remember what their abbreviations are and what it tells you when you use them in a unit conversion. All right, so let's see. So 24 milliliters is how many liters? What do I put down first? Yep, so I put down first thing, 24 ml times in a line. That's like literally always how you start, okay? Given unit times in a line. That unit goes where? On the bottom. So whatever I'm start with, so ml goes on the bottom. Because what do I want them to do? I want them to cancel. So I'm always going to put what you're given goes on the top, then put that same unit on the bottom. What unit do I want to put on top? So I always figure out my units first. Before I bother with numbers, figure out your units. So milliliters goes on the bottom end, liters goes on top because that's my answer. It's just its number. So it's just its number. So I'm not doing a proportion or anything like that. I'm not doing... It's the number I'm given, 24 ml times in a line. Milliliters goes on the bottom. The unit I want goes on top. That's liters. Now you've got to ask yourself, okay, I've got a prefix. What do I put in front of milli? Milli gets 1,000. Liters gets the 1. Okay, so you can see that up here. Milli's 1,000 times smaller. It always gets 1,000. The base unit gets the 1. So now I'm just going to cancel milliliters and milliliters. 24 divided by 1,000. Yep, decimal place goes to the left 3 places, the number of zeros in the bottom. You'll always have a calculator. But notice, like, the number itself doesn't change, just where the decimal place is. Next one. So what do I put down first? 97.1 grams goes first. Then, times in the line. What unit do I put on the bottom? Grams. What unit do I put on the top? Kilograms. So do the units first. So now I have kilograms and grams. And what's the rule with kilograms? Kilo always gets the 1 because kilo is big. It's 1,000 times bigger than a base unit. So grams gets the 1,000.
The bigger one always gets the 1. Okay.
Yep. And so for deci, centi, milli, and micro, they're all smaller. So that means the base unit will always get the 1. Okay? But kilo's the only oddball. Kilo is the bigger unit, so it gets a 1. So now, units will cancel. 97.1 divided by 1,000. Remember, you would like say 97.1 times 1. You remember if you multiply or divide by 1, it does nothing to your number. So I just like ignored the ones because it's not going to change your number. But I got to divide it by 1,000, so the decimal place goes to the left by the number of zeros. So this one is 971. Don't round. When you're doing unit conversions, don't round. I would put 97.1 in the calculator, divide it by 1,000 because 1,000 is in the denominator. Last one. 125,000. I was like, wait. Times and a line. Right? So exact same thing. Write what you're given. Times in a line. What unit do you put on the bottom in this one? Micrometers goes on the bottom. That's that funny mu. So that stands for micrometers. What unit goes on top? Meters. Okay? Anytime you see micro, what are you going to put? A million. So micro is going to get the million. That is that 1 with 6 zeros. People get this wrong just because they don't put enough zeros in their calculator. So just make sure that you like carefully count as you put them in. Because you'll like set it up wrong and only divide it by 100,000 instead, because or extra, like so the decimal place still ends up weird. So meters, it's the 1. Okay, so 1 meter is 1,000,000 micrometers. So when I do this math, what does my number come up? Okay. Now, do you notice in all of these examples, I have a base unit. I have one of my units is just a single letter, like liter, gram, and meter. So they're just a single letter. So what if I have 2 prefixed units? So this one, 4 decigrams, is equal to how many milligrams? So do you see that I have deci and milli? Well, I know what deci is in comparison to the base unit. I know what milli is in comparison to the base unit. So I'm just going to do this in 2 steps. So I'm going to still start off with my given unit. So this one would be 4 decigrams, D, G, times, and a line, just like before. What do I put on the bottom? DG, right? The unit I start with, that's always going to be the same. Whatever I start with is always going to go on the bottom in the first step. But here, I know the relationship of deci to the base unit. So I'm going to put grams on top. Because deci gets a what? 10. Grams gets the 1. So do you see, all I have to remember are those 5 equivalents, and I can do any of these. So this is going to let me go from decigrams to grams. Now I'm going to do one more step. So now I want to get to my answer, which is milligrams. So what do I need to cancel? The grams. So now my base unit, the grams that I put, goes on the bottom in this step. And my answer goes on the top, which is, and milli means 1,000. Milli always gets 1,000. Grams gets the 1. So you see that now grams and grams will cancel. Decigrams and decigrams will cancel. And now it's just a matter of doing the math. So it's 4 times 1 does nothing. 4 times 1,000 is 4,000 divided by 10 would be 400.
I have a question about the last slide. I'm sorry.
That's okay.
The last one, the 125,000, what is that, like, thing beside it?
Previous.
Which,
Micro. That
That's
funny
micro?
U. Yeah, see the funny U? So that's mu. Okay? Like that's on in my font.
okay.
I draw it with a little excessive foot on the front. I draw it like that. Well, I try to draw it like that. But that's what it is.
So it's micro to meters?
That's micro to meters.
Okay.
Mm-hmm. Mm-hmm.
So if it's bigger, would you tell it to divide it?
No. So in that, it depends on what I'm converting. So notice I'm going from grams, which is really little, to kilograms, which is really big. So see my number gets smaller? Okay? So that's, it doesn't, you put the number, set your units first, and then put your numbers in. And sometimes you'll divide things by 1,000, sometimes you'll multiply. Like if I was going from kilograms to grams, my number would get bigger. But I'm going from grams to kilograms, which is why my number gets smaller, because my units are bigger. Okay? But if you follow these steps, just follow these steps every single time. Really? That was the wrong direction. Okay. So sometimes it hits me. Nope. Next. Okay. So what about this one? 24 kiloliters is how many deciliters? So what do I put first? So I'm going to put 24 KL and then times and a line. What unit do you put on the bottom? KL. So your starting unit goes on the bottom, always. Doesn't matter what it is. It's always going to go on the bottom. And since I see KL and DL, I see those are both prefixes. So if your units are both 2 abbreviations, 2 letters after, then I know I need to do it in 2 steps. So what do I want to go to first? Liters. So I want to go to L. So what do I know about kilo? Kilo gets a 1. Liters gets the 1,000. Remember that kilo always gets the 1. It's the only prefix that's going to get the 1 because it's a bigger value. So now I got kiloliters to liters, so now I can do my second step. What do I put in the bottom in the second step? Liters. So what the base unit is goes in the bottom in the second step, and on top is, yep, the DL, the deciliters. Whenever you see deci, what goes in front? 10. Liters gets the 1. Okay? Deci gets a 10, centi gets 100, milli gets 1,000, micro gets the million. But kilo gets a 1. Then it's just a matter of doing the math. So do you see that kiloliters, kiloliters, liters, and liters cancel? 24 times 1,000 is 24,000 times 10. 240,000. You can use a calculator, it's fine. Like you don't, but all I'm doing is just multiplying all those across the top because everything in the bottom is a 1. So anything divided by 1 doesn't change. Okay, so let's do one more. 97,123 micrograms is how many centigrams? See if you can set it up. Follow the exact same steps that we did each time. You've got a micro and you've got centi, so you know it's 2 steps. Okay, what'd you start with? Okay, so you put 97123 micrograms. So that's what I started with, right? So whatever I'm starting with, that goes first, then times in a line. Ooh. What unit goes on the bottom? Micrograms goes on the bottom and grams goes on top. So if you see micro, what do you put in front? The million. 2, 3, 4, 5, 6. Grams gets the 1, right? So micro is a million. So now I'm at grams, but I got to go one more step. Times in a line. What am I going to put in the bottom now? Grams. And the unit on top? Centigrams. Centi gets 100. 100. Think of a century or think of pennies in a dollar. So that's the 100, right? Milli, think of millennium, think of 1,000 years. Like that's deci, I just think of 10 because it's a decimal place, right? Okay? Micrograms and micrograms will cancel. Grams and grams will cancel when you do this. And that's really the reason we set it up this way. So now I've got to take 97,123, multiply it times 100, and divide it by a million. Yep, 9.7123. So remember, you're just multiplying everything across the top. Ignore the ones. They don't change anything. And then divide by anything in the bottom. And in my calculator, I'll just say 97,123 times 100, and then divide by a million. Okay? So, now you get the first page. Okay? So in this like 3-page handout, so remember that the periodic table was on the last page, and we kind of talked about that. So the balancing equations was the second page. Here is a whole page, front and back, of unit conversions. Okay? So, and it's really to try and just get you into this like pattern. Because if you do this every single time, it doesn't matter if you're talking about grams, meters, or liters. It doesn't matter if you're talking about kilo, centi, deci, micro. You set it up exactly the same way. And what's really nice in metric is it's never more than 2 steps. Even if I have 2 prefix units, I don't have to figure out more than 2 steps. I always can go to the base unit and then from there to the answer that I want. Whereas, if you want to go from inches to miles, you have to go inches to feet, feet to yards, yards to miles, right? You've got to remember all those numbers. Here, you just need to know what those prefixes mean. You need to remember kilo always gets a 1, and the base unit gets 1,000. Deci gets 10, base unit gets a 1. Centi gets 100, milli gets 1,000, micro gets a million. If you can get those ones down so that you consistently use them, and that's where practicing these, you'll find that it really it'll sort of like fall in. You will see this going forward because oftentimes you will end up with unit values that you have to multiply or divide, and they're not the same units. So in this one, do you see that I have milligrams and I have micrograms? Okay, so I can't multiply. That's trying to multiply numbers of eggs times dozens. You can't, like, if I have, 79 eggs, how many dozens? So you're like 79, you got to figure, you have to like do the math to figure that out. Well, same thing here. You have to make sure that you take milligrams and convert it to micrograms or vice versa in order to be able to solve. So this will be one that we'll do as kind of a practice on Thursday. I just wanted to tell you about the last one. The other thing you're going to talk about some in lab are significant figures. And significant figures, for some people, they're like, oh, well, this is pretty clear. When we measure things, so if you like measure your height, you always have like a known amount, and then you have kind of an estimate, right? So like you might say that you're 5'5" and a half, right? Or 5'5"3/4 if you really want to try to be 5'6", okay? Or you might round it. So it really depends on what your measurements are. We will use these in lab because any number that we use in metric that's not a 0 is considered a measured or significant number. So remember when I had that 97,123 micrograms? All of those are considered significant numbers. So you would say there's 5 significant figures in that number. Zeros are really the only ones that cause trouble. And the way that you remember if a 0 is significant is if a 0 is in between. So like if I had 97,023 micrograms, that would also be 5 significant figures. If I have a 0 in between, it's considered I measured it at the 0. Okay, so in between is always significant. Right. The only other time zeros are significant is if they're at the end and there's a decimal place, like this. So 120.00, 5 significant figures in that. There's a decimal place, and all those zeros now are considered measured. What it really means is I measured it all the way down to the hundredths. So that is 120.00. I measured it down, and that last 0 is significant. So if I just say 1200, though, how many significant figures? Just 2, just the 1 and the 2. If there's no decimal place, zeros at the end, that's like saying, I'm going to win $1 million. Well, it may not end up being exactly $1 million, especially after taxes. Okay? That's an estimate. So that 1 is significant, but the other is just to show you how big the number is. The other time zeros are not significant is if they're out front with the decimal place. So that 0.001, because I could take that number and turn it into scientific notation, and that would be 1 times 10 to the minus 3. So I would drop those zeros off in front. So it's really just showing you the size of the number.
So that one only has one significant figure?
This one only has 1. That one has 1, this one has 2. Okay, so you have a pre-lab that you have to do for class tomorrow. So with significant figures and stuff, look at this, but then also like use some of the examples that you've got in your text, in the e-text in chapter 1, to be able to go back through them to make sure that you're identifying the significant figures correctly. Okay, but we will talk about this. We'll do a couple more unit conversion practices on Thursday, and then we'll also do significant figures and rounding. Pre-lab 2, right? So if you're in lab tomorrow, do not forget, get your pre-lab 2 done before class.